Okay, welcome everyone to the lab sessions for WIX1003. The lab sessions we are going to discuss about assembly language for x86 processors. And this processor they have a 32 bits and a 64-bit system. But the one we're going to look in the lab session is the 32-bit system. Okay, we'll look at the 32-bit system of these processors, and now we're going to look into what are the general purpose register we have in these processors. So they have this is a four-main general purpose register, the so-called EAX, ECX, EBX, ECX, and EDX. Then they have some other index register also. This called EBP, ESP, ESI, and EDI. So this can be used as the functions as the index register. Okay, and ESP is used for the stack pointer register. We'll look into more details on what are these kind of register functions. Then they also have a flags register, and this is your program counter. This is just like a program counter. Okay, this is the instructions pointer. Okay, so it's considered as the program counter for this processor. Then the E-flags is the condition and the status register of this processor. They are storing all the conditions on the status of this microprocessor. And they also have some few segment register, which is used for transferring data in the memory. And let's look into the general purpose register, the EBX, EAX, EBX, ECX, EDX, these four register. Actually, we can break it into half. If we break them into half, we are using it as an AX only. If you put AX, means you're accessing the lower 16-bit, right? If you put EAX in your coding, in your assembly code, means you're accessing the whole 32 bits. So the whole register you're going to access. If you put AX in your coding, then you only access the lower 16 bits of the register. You still can further divide them into 8 bits. Okay, so if you put AH, then you access the higher part of the 16-bit. If you put AL, you access the lower part of the 16-bit. Okay, so this is how you access the general purpose register. You can just change the character here, A, B, C, and D. So you access the different register. So if you want to access the lower part of the EBX register, you just put BX. Then you access the lower part of the EBX register. So this is how you access. Remember, if you put AL, means you access the 8 bits size. If it BX is 16-bit, and if it EAX is a 32-bit system. Okay, so some register have a 16-bit stamp only. So this is the ESI, EDI, EBP, and ESP. They only have can break into two, either 32-bit or 16-bit. They cannot go further down into the 8-bit system. Okay, and each register they have some special functions. So as common, the EAX, they call it as accumulator. It's just like 8051. You have a register, right? You move something, you must go through the A register. So they call this EAX is the accumulator, the most commonly used register. And ECX, most of the time they use as a loop counter. We'll look into the example how they use the ECX as a loop counter. ESP is the stack pointer. Whenever you have interrupt routines, then you need to store the context of a current program status. You need to store it in the stack location. So let's say this is a memory. This part is used for stack. Then you may this part is your instruction, right? So you're running at this moment, then they come here interrupt at this moment. Then you need to store all the program conditions of current status into the stack. So this ESP is the one which pointing to this location, to this stack locations. Okay, it's just like a pointer, point to the memory location of the stack, so that you can store the values into the stack. Then the next one is an index register. ESI and EDI is just used in the program. We will look at the example in the programs how they use as an index register. So EBP is an extended frame pointer. It's used for stack also, but it's used for extended a larger frame of a pointer. Then the EBX register is most sometimes used by the high-level language to access to the stack locations. Then the next part is a segment register. So some in our memory, they may have some sections which are used for instructions, and some section used for data, and some section used for the stack. So this segment is just to store the locations for this segment, the starting location or the base point for this sections segment. Okay. And the most important register we're going to use in the example will be those EAX, EBX, ECX. Then also the stack pointer and the ESI. So this is a few registers we are going to use most commonly in the lab sessions. The next register is the instruction pointer, okay, EIP. So this is same as the program counter we learned in our lectures. This is pointing to the locations, the number of instructions, where we are at which instruction at the moment. They'll point to the next instruction actually. When you're running the first instruction, they are pointing the EIP should be pointing to the next instructions. And the E flags is the status and control flags. And each flag will have a single binary bits to define the status. So the flag is in this here. So we have the flag such as, this is some of the status flag. The E flags register is larger than this one, but this is the most common we're going to use. The carries register mean if you're doing some operations of additions, they may need to know whether the register is able to store the addition or not. If let's say you want to add something to an 8-bit register, okay, then you plus a 1 here, so it will overflow, and if you pop 1 to the carry, the final answer should be something like this one, right? So at the end, this they will have a carry in this operation, so they will set the carry bit to 1. So in the E flags register, so let's say this is your carry bit, they will set to 1 after these operations, because the carry is set to 1. Same thing, go to overflow. If the register is overflow, then it's also the overflow register bit will set to 1 also. If not, they will remain at 0. So this status register is telling you what are the result of the operation you just works on. Same, go to the sign bit. If you're doing some operation, you do a subtraction or do a subtractions, then you using 2 minus 3, then you get a negative 1. So it's a negative value at the end. So the negative bit was set to 1. The sign bit was set to 1. Okay. Then 0, the same thing. If you're using do operations 2 minus 2 equals to 0, the end result is 0. The 0 bit will also set to 1. If you are doing something which is not so, if this operation is negative values, then the 0 will remain as 0 bit. The bit is equal to 0. This one is the carry for 4-bit operations. Okay, as long as the 4-bit operation they have a carry to the bit number 5, then they will give you 1 in here. From carry bit 3 to bit 4. Yeah. Then the priority bit is to check the result of your operations have even numbers of 1 or not. So let's say you're doing operation, the end result is 1011, 1010, 1111. Then they will check whether you have even number or not. So 1, 2, 3, 4, 5, and 6. You have 6 1 in here. So the priority bit was set to 1 because they're looking to the even number. So if the 11010000 is an odd number of 1, then this bit is equal to 0. Okay. So this status flag is very important when you're doing some comparison. So we'll look at the example later on. Okay, so now let's look into the examples of the assembly coding. So please go to this CSA Padlet link. This Padlet link, padlet.com/oxus/cs1. So in here, we're going to start to use some example coding in assembly for this x86. So in here, we give you all the possible some of the instruction we commonly use to complete your lab assignment. Okay, so the first one we're going to look at is the move instructions. So move is just like your the instruction you did before. You're moving something from one location to the other. So you move from the source to the destination. So it's, in high level, it's just equal. It's something like this. Your destination is equals to your source. So that's all. So this is the example programs. So the same thing, you just open up the Visual Studio Project 32. So you just open this Visual Project 32 Visual Studio 2019 folders, then open this VC++ project. Okay. So after you open up your VC++ project, you just double click this add sub to ASM file. Then you come to this here. Then you can copy the code in here. The first example. You expand it and you can copy the whole coding and put it into here. So remember, the necessary part of coding is the first one is include irvine32.inc include file. Okay, remember we download two files in the beginning of our lab sessions. We download the project 32 folders and another one is called irvine folder. So the irvine folder basically consists of this library.inc. So that's why you need to put that in the C drive of your the system drive of your computer. So include irvine32.inc. Okay, then the other part is the close of this program is exit man emp and man. So this is the necessary part of the program. The middle one you can delete also, okay, but they're still able to run. So these two is the necessary, the opening and the closing of the program code. Okay, then in the middle is the sections of dot data and the dot code. So dot data means you define the variables here. So you define all the variables in the dot data sections. Then the dot code means your main program. Okay, you have the main program here, starting at this two line is your, after the main program is your starting line. Okay, so remember in the example, I may just give you the example coding, something like this one. Let's say this example, you want to copy this one, you need to copy it and you need to paste it in between. Okay, you don't overwrite everything, then you don't have the include and the and, right? So you just copy it, put it at the between of this include and exit. That's all. Okay, so it will work. It will work if you put this way. If you delete these four lines, then it will not work at all. Okay, so this is the first example program. So when you want to build, you just click the build and build projects. Okay. Okay, so you can see there's an error. So there's giving you 4 errors here. So let's look at it. What is the error meaning? So you have an invalid instruction operands. If you want to know, you just double click these sections. They will point to you. This is the invalid instructions. Okay. So why is it invalid? Because move is only able to move from register to memory, memory to register, or register to register. They are not able to move data between variables. So I want to move variable 1 to variable 2. So it is not possible. So that's why it's not working. So you can just move var1 to your EAX register maybe. Okay. Then the next one, initialization magnitude too large for specified size. Then when I double click, it points to here. So there's a word. Then this one is this thing. So yeah, in your assembly here, they have certain, when you define variables, you can define. They didn't put it in here. So when you define variables, maybe I open up. when you define variables, there can be something like this one. Hold on, change the pen. Okay. You change the code when you define variables. There's a few types on it. It can be using byte, word, double word. Okay, this is the byte, word, double word. Yes, so if it's byte, then it's used for 8 bits. 1 byte equals to 8 bits. You are defining an 8 bits data. If it's a word, then you are defining 16 bits data. And if it's a D word, you are defining a 32 bits data. So now let's look at this example. You're defining a word. So a word is equals to 16-bit here, right? So it must be within 16-bit. But now how many? The hash means hexa. So this number is hexa number. So 1, 2, 3, 4, 5, 5 digits of hexa number. Total is equals to 1 digit equals to 4 bit in binary. Right? For that here is 20 bits. It's over the maximum available 16-bit by using words. So you cannot define it by using words. It is 20 bits. You have to change this thing to D word, double word, so it's 32 bits. Then it should be words. Okay? So you can try to build again. So you can see the build is succeeded without fail, right? No error happened. Okay, so remember, when you define variables, the size have to be matched with the size you define it here. Okay, so if you define a byte here, then the maximum value you can put in is 8 bits only. If you define a word, the maximum value you can assign to it is a 16-bit. So D word is for 32 bits. Okay, so let's say I move something variable 1 to my AX register. So let's see what happened. Error again, right? Instruction operands must be the same size. So my VAR is D word, which is the 32 bits, right? D word is 32 bits. Okay. And remember, I want to move it into my AX. So what is the size of my AX? If you refer back, the AX is 16-bit only. So that's why it's not, you cannot move something is 32-bit, you want to put into a 16-bit location. So it's not matched. So that's why they're telling you it's not the same size. So whenever you find the arrows, don't panic. You can just double click. They will show you which line having error. Then you just go and check the line. Okay, so that's why I need to use the whole register EAX and to build it. Okay, so this is the example of a move program. And if we want to look at how the program run, we want to go through line by line. So let's say I want to move EBX, move the EX to EBX. This is another functions called dump register, which they will display all the register value for use. This is the function included in this Y32. Okay, call dump rex is mean call out, display out all the register for you. We don't use this one here first. Okay, so let's say I have two lines here. I move VAR into my EAX, then I move EX to EBX. So let's build, see is it working. So it's working, the code is correct. So the next step, if I want to go through step by step the coding, I can go to the debug mode. Then I can see the step by step. So before we go into that, we need to put the breakpoint. So you need to come to this bar here, the gray color bar here. You need to click on it so that a red dot is coming. So this means the breaking point. So the code will run when you compile. They will run from the first line up to here. When they see the red dot, they will stop here. Okay, so you need this red dot only. You can go into the debug mode. Okay, and stop there. If you don't have the red dot, they will just run through and end. Because you didn't put a breakpoint, they won't stop, they just debug through, that's all. Okay, so if I go to the debug mode, I start the debugging, then they go in, debug, then they run the code, that's all. They come out from the debug mode. Right, so you can see it come back to the normal conditions, right? So you need to put a red dot. Remember, when you want to go into debug, you must put the red dot. Then you only start debugging. Then they will come to here and stop. You can see there's a yellow arrow in this red dot. So now it's pointing to the location you are. I'm stopping at this line. Then this telling what happened, how many CPU usage in here. But this one is don't need to look at it. The Diagnostic Tools. So if you have this thing, means you're in the debug mode already, and you have the arrow in this breakpoint. So you go into debug, and you can pull up the windows. Okay, so the most common window is the register windows. So you can see all the register values in here. Right, the register we just studied before in the PowerPoint slide. Okay. The second window is the memory window. We want to look at the memory. So I have two, so I can pull this out to put it side by side, right? I can put it side by side. Just pull it out, then you can see there that you can point to here is at the up, point to here is the left, at the bottom, right? So I want to put side by side, just put it here. So now it's at side by side. Okay, so now I want to move VAR1 into my EAX, right? So now our EAX is this random value as reboot condition is at this random values. So I want to see what happened after I move this thing. So this I just step over, right? This signal step over. Then they will execute this code and they come to the next line and stop here. So you can see my EAX change to these values. So the thing here is also in hexa, 32-bit EAX in hexa value display. So it displays this thing for you, right? Then the next line is move EAX to EBX. So your EBX is here. So I just step through. You can see your EBX change to this value also. Then it said exit. So I step through again. It will go out from the debug mode because you ask them to exit. Okay. So this is how you look at the debugging. So let's say I go into debug again. They will come here and stop again. So I just start and start. So both registers same value now. Okay. So let's say I want to look at the VAR1. This thing dot data I define variables. They will store in your memory, right? So I can just using this and symbol start VAR1. Okay. Then they will bring me to the location storing this VAR1. Remember the and symbol using the and symbol. This symbol followed by VAR1 and put it in your Windows of this address locations. I put the and symbol VAR1, then they will bring me to here. So you can see it's storing at this location 0x00404000. So this is the memory locations where you store the values 1000, 10,000 here. Yes, okay. Then this is the next values. You store the 20,000. Yeah, somewhere here. Okay. You can using the memory window and the register window to do the debug. So after you have tried this code, you can try the other coding in examples. So this I want to try example 2. Run the move. Okay. So remember, I'm just giving you the coding here, so you just copy it here. So remain the move. Move VAR1 to VAR2. So this one. So you just build it. So you see the error. So operand is not the same size, right? D word and AX. So you can either change it to word or I need to change it to EAX. So if I change it to word 16-bit, then I need to reduce the size of the variables. Okay, then I think it should be okay now. Just build. So succeeded. And you can start without debugging also. When you do start without debugging, they will straight away run through this program without debug. Okay. And they will call out this window, right? So I told you there's a call dump rec. Edit. Okay, so this is the call dump rec. So in here I call out the dump rec. So means after I move a variable 1 to variable 2, I call to dump this register. Okay, so my EAX is in these values, which is equal to variable 1, right? AX is equal to 1000 here, right? Then the second one is the variable 2 into DX. Then I call dump rec again. So my DX is equals to 2000 should be. EDX equals to 1000. Why? Variable 2 call dump rec. Yes, correct. Again, so let's see. Because I removed my VAR1 to VAR2, so my VAR2 now is also equal to 1000. Then I move my VAR2 to DX again, so my DX should be 1000 also. Yes, correct. Right, so this is the examples how you move the values from one memory locations to the others. You must go through a register. You cannot direct move from VAR1 to VAR2. Okay, so this is how you move from one memory locations to the other locations. And you can try the next examples. This is to teach you how to define the byte word D word in this example. So you can try it by yourself how this thing happen. I define a byte of word D word, then I try to move it into a different size of register locations. Byte should go to AL, one word should go to AX, one D word is go to EAX. Okay, the next sessions you're going to look at is the move with extend, sign extended. Okay, so I can move with sign extended. Okay, let's say copy this one. I'll come back to here and copy in here. Okay, I have a data dot count word. They are using -6, so this is a -6 values. Then I have a move 0 into my ECX, then move my count into the CX. Okay. So I debug. Start without debugging because I want to see the output. So this is the output. Your ECX, CX should be equals to the count, right? CX equals to count. Your CX is FFFA. So it's a negative values, right? It's FFFA now. So ECX, the beginning is 000 because we move 0 into the ECX, right? So at the beginning, so let's redo one call dump rec again. And start without debugging. So you can see you move 0, so all the ECX equals to 0. Then the second portion, you move the negative value into CX, so CX become FFF6. So this is the two complements values of -6 equals to FFFFA. Okay, so when you, if let's say I want to extend everything into the whole ECX, I can using the move SX into the ECX. Right, so now I'm using word. If I'm using move, I'm unable to move something into ECX. I'm only move to CX only because they need to be the same size. Right, so if let's say I move CX, you can try to build, you'll get error. Same, they were telling you the operand is not the same size. So what can you do is to using the sign extended. So let's say I start without debugging, they will build it. So successful. So you can see I extend the sign bit to the whole ECX register. Right? Initially I move 0, then I move the count, which is a -6, into here, which is equals to make it become fully sign extended. Okay, so how to explain this thing? So let's say I create new slide. Okay, so here, so -6 is because I'm using word and I move it into a CX, so the CX is 16-bit, so the 16-bit become this one, right? So it's equals to 1. Okay, so CX is a bit long, so let's say I change the coding to become byte. Okay, let's say this is byte. Then I move it to CL only. Right? It will only CL because of FA only. Okay, so let's say if you decode, you can see your CL, yeah, this 8 bits equals to FA, right? So because I'm using CL, because I'm using byte, so I'm moving into CL only. So you can see if I moving in is using a byte and I move it into the CL, so the CL equals to FA, which is a 1111. A is a 1010, right? How to get back the actual values? This is 2 complements, means invert and +1. You will get the actual values, right? 0, 1. So this is equals to 6. So this is the 2 complements of 6, which means -6, right? So if you put it in the word, they are the same. If this is extra 1 only, right? 1010. When you invert it, you will get back the values also, right? 0101, which is equal to 6 plus 1. This is equal to 6 also. The other is all is 0, right? So this is the functions of extend. So if I want to put it in the ECX, the whole thing, I can just using move SX. Then I will extend the F for you. They'll extend the sign bit to the rest of the bit in this whole ECX register. Okay, so this is a function of sign extend. If I'm the positive value, I have a 0, then they will just extend the 0 for you. So let's say we go back. This is a 6. Then we start our debugging. Yeah, so they will just equal to 6 only. So let's say I don't want to move 0 into here because I just want to let you know what is the value. So let's say initially this is CL is equals to AA, right? CL equals to AA here. You see? Then I move the count into my CL. It is 06 here. So let's say I want to sign extend, and the CL has a random value at the beginning. So let's say I want to sign extend, move it without debugging. What happened? Oh, sorry, not extend to CL, CX. If you extend, it means extend to the whole big register. Okay, so you can see the extend the 0 for you also. It becomes 6 here. Previously, there's a random number here. They extend the whole ECX becomes 6. So sign extend means they will extend the sign for you. So if your sign is 1, they extend all become 1. If your sign is 0, they extend all become 0. So this is the function of sign extend. Okay. Then the next part is 0 extend. There's another one called 0 extend. So in 0 extend, they don't care what is your sign. They will just extend everything becomes 0. Okay, so if you copy this thing, 0 extend. Okay, so we don't need to copy. We're just using back the one. 0 extend means x. So let's say I want to 0 extend. So let's say this is -6. Then I want to using 0 extend. It's byte only. I want to extend the 0 at all the rest. So if it's negative, suppose if sign extend is supposed to extend 1, right? But now you can see they didn't extend the F anymore. They just extended, put it all 0 here. So 0 extend means I don't care what is the value. I just put the all the front bits become 0. So let's say you're dealing some unsigned variables, unsigned values. This is FA is a certain values. You don't want it to extend the signed bit for you because you are not working with the negative value. You want to have some fixed number. So let's say I want to deal with values FA, right? Value F. Value F. Let's say values in hexa 82 hexa values. So 82 if in hexa it should be equals to 82, right? This is 82. So in hexa is in binary this one, right? This is binary, this is hexa, right? So in binary is equal to 100000110, right? So the sign bit is equal to 1. So if I'm using sign extend, it will extend it for me. But now this is not a negative values, right? So if I'm using sign extend, you can see they will still extend it for you, right? 82, then they'll extend the sign for you, become FFFFF. So you get the wrong values at the end. Okay, so if you want to work with unsigned values, you just put it as a 0 extend, then they will do it for you to extend all it become 0. Okay, so you get back 82 in the whole ECX register. Okay, so it has to be clear. Sign, they'll extend the sign for you, no matter they don't care what is the value, whether it's negative or positive. As long as the last bit is 1, they will extend it for you. Since this 82, the last bit is equal to 1, so they extend it for you also. Okay, so be careful of the sign extension also. Then I think this is the 2 you need to know. Yeah, the next one is you can call out the status register by using the LAHF. Okay, so if you do this LAHF, they will load the lower byte of the status flag to your register. So they will load the lower byte, which is 0 up to 7 here. So all these things they will load into your AH. So let's try the coding. So let's say I change this thing to LAHF. Okay, then I debug. So you can see your AH previously is FF, now it becomes 46. So they are loading the status flag into this 46. So it means your status flag equal to 46. Let's look at it. This one, status flag 46 equal to 0010. So your 46. Okay. Let's. Okay, so let's look into here. This is the bits of the status flag lower byte. You are at 46, right? The value is 46 hexa, which is a 0100 0110, right? So your bit 0 is a carry flag. So this is your carry flag. Then this is your second bit is your parity flag. So this is first 0 first. Second, this is your parity bit, parity flag. Then 3, 4, this is your series AF flag. 5, 6, this is your 0 flag. 7 is your sign flag. Okay, so if you refer to your call down register here, they will call out your status flag here also. So the AF is 0, right? Correct. The PF is 1, right? Then your CF is 0 here, right? Then your ZF is 1, your SF is 0, right? So this will help you to call out the status flag by using this LAHF also. And you can also using a call dump to call out the status flag values here. Okay, so if you don't want, you can also using this LAHF, then you'll bring the values into your AH register. Then the next one is SAHF, means you store back the values into the status flag. You can modify the status flag values by using this program. You store the AH back into the register. So let's say I modify the coding, I move. Okay, I move it, I move the AX, just move AX equal FF on it. Set it all equals to 1, right? Then let's see SAH. Let's see what happens. Debug, start the debugging. No, what happened? Oh, sorry. So if you are using this assembly, you cannot put the same as your previous x05 program. You cannot put character directly. You need to put a 0 at the beginning. So if FF. Okay. So you can see AX, they store AX into your status flag. Your AX is FF. Oh, I did something. AX, so is not. I should move into AH instead of AX, because AX is a 16-bit, so it should be AH, right? I want to modify the upper byte of the AX. So you just start decoding. Undefined. Oh, again, sorry, it's 0 here. So this one. So the AH is a FF. Then you can see I move everything become 1 already, right? CF is initially 0, then I modify it become 1, right? The AF become 1, the PF become 1. So the thing we can modify in the lower byte is just this few, because they're at lower byte. So this is the few where priority bits, the flag we can modify by using our coding only. So this is how we do it. Okay.